From space, Earth appears as a spherical object with surface features dominated by water. Most of that appearance comes from the large amount of water that covers about 70% of the surface. We drink it, we swim in it, we depend on it, and yet its true origin is still not fully clear. For a long time, many people assumed Earth's water was simply always here. It feels natural to think the oceans are as old as the planet itself. But when we look closely at the early history of Earth, that simple picture starts to fracture. Billions of years ago, young Earth was more like a glowing rock in a storm of debris. Temperatures were high, impacts were frequent, and any surface water would have evaporated into space. This raises a quiet but deep question. If early Earth was so hostile to water, how did we end up with oceans? So what is the big mystery we want to understand? At its core, it is a question about origin and balance. Did Earth form already loaded with water locked deep inside its rocks? Or did most of our water arrive later, carried by icy visitors from the outer solar system? Could the answer be a mixture of both ideas, stitched together over hundreds of millions of years? This is not only a story about chemistry and space, it is also a story about why our planet can host life at all. Liquid water shapes climate, carves landscapes, and flows through every cell in our bodies. Without water, Earth would be closer to a bare, dry rock like Mercury. With too much or too little, our climate and geology would look completely different. So understanding where Earth's water came from is also a way of understanding why we are here. The puzzle sits at the intersection of planetary science, astronomy, and geochemistry. Each field brings a different clue, from meteorites in laboratories to distant comets in telescopes. Piece by piece, they help us test whether our oceans are a local product or a cosmic delivery. It is a calm mystery, not a dramatic one. Every glass of water, every cloud, every wave is a quiet reminder of a very old question. Where did all of this come from? And why did it gather here, on this particular world? Earth did not begin as a calm or familiar world. It formed in a crowded neighborhood of young stars, drifting dust, and growing planets. In that setting, heat and gravity shaped everything, including the earliest hints of water. To understand the timeline, we step back about 4.5 billion years. Earth was assembling piece by piece from rocky fragments. These fragments came from different regions of the solar system, each carrying its own chemical signature. Why does this matter now? Because those chemical fingerprints help us trace whether water was present from the beginning or added later. If the building blocks of Earth were already rich in water-bearing minerals, we would expect traces of this in today's rocks. When scientists examine ancient minerals, they sometimes find tiny amounts of hydrogen trapped inside them. This hydrogen can act like a timestamp, revealing conditions from the planet's earliest days. It offers a quiet clue that water may have been stored deep inside Earth's interior from the start. But the outer solar system played a role as well. Comets and icy asteroids move through space like frozen archives. Their chemical composition tells us something about the materials available beyond the Sunday's warm zone. What does this tell us about place and scale? It shows that Earth sits at a crossroads in the solar system, close enough to the Sunday to be warm, but still positioned to receive icy material from farther out. Over time, impacts, volcanic eruptions, and atmospheric shifts shape the water we see today. Even now, new measurements continue to revise our picture of early Earth. The context is complex, but each new sample tightens our map of when and where Earth's water story began. Imagine heating a metal pot on a stove. As it warms, water trapped in tiny gaps can escape as vapor. This simple idea helps us picture how early minerals could release or retain water under intense heat. The core mechanism begins with hydration in minerals. In everyday terms, this is like a sponge soaking up moisture, except the sponge is solid rock. Atoms of hydrogen and oxygen slip into the crystal structure and remain there as bound water. The technical definition is more precise. Hydrated minerals contain hydroxyl groups or water molecules locked inside their lattice. These groups stay stable until high temperatures break the structure and release the water. This mechanism matters because young Earth experienced extreme heat. If the planet formed with hydrated minerals, much of its water could have been stored deep underground. Over millions of years, volcanic activity could release that water into the atmosphere. Now we compare this with another mechanism, one many people imagine first. Picture snowballs hitting a hot sidewalk. Most melt, some evaporate, but they still deliver moisture. In space, icy bodies behave in a similar way. When comets or icy asteroids strike a planet, they transfer some of their water. The rest may escape as vapor, but repeated impacts can gradually build a reservoir. Both mechanisms operate through transfer and release. One comes from within Earth's rocks, the other from outside visitors. Together, they describe how water can accumulate even in a harsh environment. Scientists rely on a set of observations that act like anchor points in this story. Each one offers a measurable clue about how water formed, moved, or survived during Earth's early history. Together, they create a pattern that is steady, even if not yet complete. First, hydrogen isotopes in Earth's oceans match those found in certain carbon-rich meteorites. This means the ratio of heavy to light hydrogen is similar, suggesting a shared origin. It implies that at least part of Earth's water came from asteroid-like bodies rather than comets. Second, volcanic rocks contain small but measurable amounts of ancient hydrogen. These samples come from deep mantle sources that have remained isolated for billions of years. Their composition hints that water was present inside Earth from its earliest formation. Third, measurements of comets reveal isotope ratios that often differ from Earth's oceans. Some comets carry too much heavy hydrogen to be a primary source. This suggests comets likely contributed, but not enough to explain all of Earth's water. Fourth, computer models show that during the early solar system, asteroid impacts were far more frequent than comet impacts. This pattern changes how we weigh the contribution from each type of object. If asteroids were more common, their water delivery becomes statistically more significant. Fifth, laboratory simulations demonstrate that hydrated minerals can release large amounts of water when heated. This process occurs during volcanic eruptions and mantle melting. It shows that internal release could supply a long, steady flow of water over geological time. What do these observations mean when combined? They point toward a mixed origin where both internal storage and external delivery played a role. The exact proportions remain uncertain, but the evidence consistently favors a balanced explanation. The null hypothesis in this question is simple. Earth's water might not require any special or exotic explanation. It could be the natural outcome of ordinary planetary formation, without needing large contributions from distant icy bodies. To test this idea, we evaluate each proposed mechanism on its strengths and limits. The first mechanism is internal origin. Then water release through volcanic activity would be expected. Where does this work well? It fits with deep mantle samples that contain ancient hydrogen. It also aligns with models showing that minerals can store significant water during high-pressure formation. Where does it fall short? Internal sources alone struggle to account for the sheer volume of water in Earth's oceans. Even optimistic models reach only a fraction of the roughly 1.5 billion cubic kilometers we observe today. The second mechanism is asteroid delivery. Carbon. Rich asteroids contain water and hydrogen isotopes similar to those in Earth's oceans. Their early impact rates were high, making them plausible contributors. Where does this explanation succeed? The isotope match is strong and repeatable across different studies. The numbers also support it. Because asteroid impacts were frequent enough to supply large quantities of water over time, where does it weaken? Asteroids alone might not explain mantle hydrogen that appears older than many surface sources. This suggests some water existed before most external impacts occurred. The third mechanism is comet delivery. Comets are rich in ice and often proposed as the main source of planetary water. However, their hydrogen isotope ratios vary widely. What works here? Comets could provide bursts of water during rare but energetic encounters. They might also explain certain organic molecules found on early Earth. What fails? Most measured comets do not match Earth's hydrogen isotope ratio. Their contribution appears real but relatively limited. When examining these mechanisms together, the overall pattern becomes straightforward. Internal storage likely provided an initial baseline of water. Asteroids added a significant amount during the early bombardment period. Comets contributed some material, but not enough to dominate the picture. Based on current evidence, the explanation that aligns best with measurements is a combined scenario. Water originated partly from deep within Earth, and partly from water-bearing asteroids, with comets playing a smaller supporting role. Our knowledge of Earth's water remains limited by the tools we use to study it. Rocks from the deep mantle are difficult to access, and only a small number reach the surface unchanged. This means our samples may not fully represent the interior, leaving gaps in how we interpret ancient hydrogen. Space missions add important clues, but they face their own constraints. Most comets and asteroids have never been directly measured, so we rely on a small group of well-studied objects. If those samples are not typical, our conclusions could shift as new data arrives. Laboratory simulations also carry uncertainties. We recreate high pressure and high temperature conditions. Yet these setups simplify a far more complex early Earth. Small differences in temperature or mineral structure can change how much water is stored or released. Our isotope measurements are precise, but not perfect. Tiny variations can alter our understanding of how closely Earth's water matches that of meteorites or comets. Improving sensitivity would help detect subtler patterns hidden inside ancient samples. What kind of experiments could close these gaps? A mission that returns pristine material from different classes of asteroids would give a clearer picture of early water sources. Deep drilling technology, capable of reaching the lower mantle, could reveal how much water remains locked inside Earth. High-resolution telescopes could study comet families with greater detail. By observing their isotopes across a wider range, we could refine estimates of their contribution. Together, these steps would tighten the boundaries of our models and reduce the uncertainty in this long-standing mystery. If Earth's water story is correct, it reshapes how we understand planets both near and far. A mixed origin suggests that water can form under a wider range of conditions than once assumed. This broadens the possibilities for life-bearing worlds, especially around stars very different from our Sun. One impact is scientific. Planetary models would need to account for both internal and external sources of water in their early stages. This could change how we evaluate exoplanets, shifting our focus from perfect conditions to adaptable pathways. Another impact is technological. Future missions may prioritize sampling asteroids rich in carbon and hydrated minerals. These bodies could hold the key to understanding not only Earth's water, but the chemistry that supports life. A third impact reaches everyday life. If asteroid-derived water turns out to be common, it strengthens the idea that resources for long-term space travel may be found near Earth. This would influence how we prepare for human exploration and the infrastructure we build in orbit. But there are risks in how we interpret the science. If people assume one mechanism is proven, while others are dismissed, the narrative becomes misleading. Clear communication is essential to prevent the impression that a single discovery solves the entire puzzle. There is also the risk of overstating certainty. The volume of Earth's water and the complexity of isotope data make this a gradual field, not a dramatic one. Each finding must be weighed carefully and placed within a broader context. At the scale of the solar system, the origin of Earth's water is a quiet reminder of how many processes work together. Nothing in this story depends on a single event, but on long, steady interactions across space and time. Understanding these interactions helps us read the history written in every drop of water on our planet. The excitement is real, but so is the need for caution. Earth's water is a reminder of how complex and delicate planetary histories can be. Even simple questions often hide long chains of events shaped by heat, chemistry, and chance. If the mixed origin model continues to hold, our understanding of habitability will expand. It will show that water can arise through different paths, not just one rare alignment of conditions. That makes the search for life beyond Earth both more hopeful and more grounded. Where does this leave us now? It leaves us with a deeper curiosity about our own planet. Every ocean wave, every raindrop, and every river carries the memory of processes older than Earth itself. A final thought opens the door wider. If water can appear from both inside and outside a forming world, what other ingredients of life might follow similar patterns? This question stretches from our oceans to distant exoplanets, linking us to worlds we have not yet seen. If you found this topic intriguing, subscribe to the channel and share your thoughts in the comments.